Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's biweekly contest, most profitable path in a tree. The problem states that you are given a tree, each node of the tree has a value associated with it. Okay, um, whoever reaches that node first, like there are two players in the game, Alice and Bob. Whoever reaches that node first will get that much amount. So the amount can be positive or negative as well. Okay. Now, as said, there are two players, Alice and Bob. Alice will start at node 0. Bob will start somewhere below, some let's say at node 3. The initial position of Bob is given, and Alice will always start at node 0. Now, Alice will move downward and will end the journey at any of the leaf node. Bob will move upward and he will end the journey at root node, that is 0. Now, if there is a node where Alice reaches first, she will get that much amount, or whether it is positive or negative. Similarly, if there is a node where Bob reaches first, he will get that much amount. And if there is a node where, let's say, Alice and Bob both reaches together, then the amount would be split between Alice and Bob, irrespective of whether the amount was positive or negative. So they both will either gain equally or lose equally. Now, you can there are multiple possible paths that Alice can take or Bob can take. You need to find out the maximum, the optimal path that will give Alice the maximum income. Okay. Now, one more constant here is, let's say there is a node where Bob already visited. Then, if Alice visited that node again, she will not get anything. So, let's take an example. Let's say this is the tree. -2, -4, 2, -4, 6 are the values of each of these nodes. Alice will be at 0. Let's say Bob is at 3. Now Bob will move upward and Alice will go downward. So there is only one choice for Alice, that is to go at. So initially the score of Alice is -2, the score of Bob is -4. Now there is one choice of Alice. Alice will move to 1, right? And similarly there is only one choice of Bob. Bob will also move to 1. Now because Alice and Bob both reaches 1 simultaneously, this 4 will be splitted between them equally. So Alice will get 2, Bob will get 2. So initially Alice's score was -2. Now plus, there is a gain of 2. So total score is now 0 for Alice. And for Bob it is -2. Now there are two choices with Alice, either to go at 2 or to go at 3. So if Alice go at 2, then this was the path. Here Alice gain -2, here the gain was 2, and here also the gain was 2. So in total this path, if Alice chooses this path, the maximum income would be 2. Now next alternative could be Alice took this path. Now if Alice took this path, the gain here is -2, gain here is 2 because it was split. The gain here will be 0 because Bob already visited this node once. So it Bob will not, like Alice will not gain or lose anything at this node. So -2 plus 2 plus 0 and then plus 6. So in total the maximum gain of Alice in this particular path is 6. And because 6 is greater than 2, this is the result. Okay. So hope you got the question correctly. There are two important things. If there is a node where one of the one of the player visited, the other player, if they visit again, they will not gain anything. If there is a node where they both reaches simultaneously, the amount will be split, and you have to find the optimal route for Alice. Okay. Now there are a lot of moving pieces in the problem. Like even explaining the problem requires 4 to 5 minutes of time, right? So let's try to break it down as always. So let's assume that there is no Bob at all. There is only one player, Alice, and we have to just find out what is the optimal path for Alice. Optimal path as in what is which root, which leaf node Alice will end up in, right? So again, I haven't shown the values of each of these nodes just to uh, make things clear. Like, so now think about it. We have to just find out what is the optimal leaf node for Alice. Leaf optimal as in the gain would be maximum. Okay. Now, in any kind of this question, you or any kind of tree question, the first thing that you should try to solve is try to solve the problem for a single node. Okay. And if you are able to solve the problem for a single node, try to solve the problem for a three node and then move forward. Like, you will get the idea, because you can build a recursion using this approach. Okay, so let's try this approach. Let's try to solve the problem for a single node. Let's say there is only one node and Alice is here. So what is the maximum income for Alice? Maximum income would be just the value of this node, right? That's it. There is no other. Like, this is the leaf node and Alice is at leaf node. So that's the end of the journey. And the value or the income of Alice would be the value of this node. Okay. So we solve the problem for a single node. Now, because we solve the problem for a single node, let's try to solve the problem for a three node structure. Okay. So we know the value of this particular piece, right? Like, we know the value of this node. Like, this is the only node in the tree, we know the answer. If this is the only node in the tree, we know the answer. But now this is the root, like, right? So if this was the root, we know the answer. If this was the root, we know the answer. But now this is the root. So Alice would either go left or go right, right? Now, which one Alice will took? Which path Alice will took? Alice will took that path which have more, or which have maximum value at the next node, right? Because there is only one node here. So in essence, if there are n such nodes, right, Alice will just find out the maximum across all those n and just go there. That's it, right? So that's exactly what we will be doing here. We know the answer for each of these child node. Let's say this is the root, like this is a tree. This is the only tree that we have. If this is the only tree that we have, we know the answer. Similarly, if this is the only tree that we have, we know the answer. The answer will be the value of this node itself. Now, if there's one more tree, one more node here, what will be the answer? The answer would be just take the maximum of these two nodes, or like these two values, and add the value here. Okay, so let's take an example. Let's say the value of a value looks something like this. Okay, -2, 3, 4, -3, 2, -2, 2, 4, 1, and 6. Okay, so let's solve it for each of these. So what is the value of this node? The value of this would be 1. By a value of a node, I mean if that is the only node in the tree, what is the maximum, what is the optimal path for Alice? So because there is only one node in this particular tree, the value would be 1. Similarly, there is one node in this particular tree, so value would be 1, right? Now, let's say this is the tree. Now, if this is the tree, what will be the value? Value would be -2 plus the maximum across these two. So the maximum across 1 and 1 is 1. So -2 plus 1 is -1. So value would be -1, right? Similarly, you know the value of this would be 3, because this is the leaf node and there is only one node. So that is the gain. Similarly, all the leaf node, you already know the answer. So let's just fill all those leaf nodes. Now, what is the value for this? The value for this would be 4 plus the maximum across this and this. So what is the maximum across this and this? -1 and 3. So now this is an interesting thing. You already know the value or the maximum across this entire tree, right? So you don't need to traverse every path here. You already know the maximum across this entire tree. So which is -1. So you can just say, I know the maximum across this entire tree, and I can just convert this entire tree into a single node with a value -1. Now the problem is very similar to what we just solved. So there are only two nodes, two child nodes, and there is one parent node. Now what will be the value of this parent node? 4 plus maximum across all the child, which is -1 and 3. So 4 plus 3, which would be 7. Correct. Similarly, what is the value of this? The value of this would be 2 plus maximum across this, which is 2. So 2 plus 2, which is 4. Right. Now, what is the value of this? So to calculate the value of this, -3 plus the maximum across all the children. There is only one children here, so you have to take that. So 4 plus -3, which is 1. Now, similarly, the value for this would be 5, 4 plus 1, because there is only one children. Now, what is the value for this? Sorry, 6 would be outside, right? So what is the value for this? The value for this would be 6 plus the maximum across all the children. Why maximum? Because this 7, basically you can convert this entire subtree into a single node with a value 7, right? Similarly, you can convert this entire subtree into a single node with value 1, and this entire subtree into a single node with value 5. So what is the maximum across 7, 1 and 5? 7. So 7 plus 6, 13. 13 is the maximum value for this node. Okay, so I hope you get the solution where Bob doesn't exist. So what we have done, we have just simply said that we need to find out what is the optimal path for Alice. Now, to find out the optimal path for Alice, what we have done, we found out the optimal path for each of the node, assuming that that particular node is the root of the tree. Okay, so we started with single node. For single node, if this is the root, we know the answer because this is the leaf node. Now then we said that, okay, now the tree contain three nodes, or basically one parent and x number of children. Now what? So we just verified that if that is the case, it always makes sense to move with the children which have the maximum value. Okay, so we once we solve this kind of problem, we said that any subtree can be boiled down to a single node with some value. So now uh, solving the problem for a particular root x means solving the problem for each of the child nodes first. And once you have the value for each of these child node, you can forget about all the subtree because you can replace the subtree with that particular node value and just take the maximum across that particular values. Okay, so what would be the pseudocode look like? Pseudocode would be something like this. So you have to calculate the best path to live, right? What you will do, you will start with a, like this root would be 0 initially, which is the point a. Now if the root is like if the current node is a leaf node, then you already know the value would be simply the value of the current node. Now if the node is not a current node, the value would be the value of current node or the root node plus cost. What is cost? Cost is maximum across all the children. Okay, so what we have done, we have iterated over all the children, and like this is just a safety condition, you can ignore this. Now after that, we calculated the value of the children by calling the same function, right? And once we have the value for the children, we just take the maximum across all the children. And finally, what is the value for the root? The value for the root would be cost, which is the maximum across all the children plus the current value of the root. Okay, so hope you get the clarity how to solve the question if Bob would not have existed. Okay, now once we have solved solved this particular piece, the rest is very simple. Let's try to discuss that. So let's say uh, okay, let's remove some of these stuff. Okay, now let's say this there, like Alice was there, and we already know the value of each of these node. Like what will be the maximum possible path of the leaf if we start from a particular node x. We already know that value. We just calculated it previously. Now let's say Bob is there. So think about it. Bob has only one path, right? Bob will only go upwards, and there will be exactly one path for Bob. Bob can't take multiple paths. Now Alice has choices. Alice can like take this one, or take this one, or take this one, and so on and so forth. Alice has choices. Now what all like clearly we can't iterate over all the childrens, right? That is not possible, because that would mean that we have to consider all we have to consider all the leaf nodes, and then calculate the contribution of Alice and Bob in each of these nodes, and then calculate the new cost. So that is not possible. So what exactly you have to do? Because Bob has only one path, right? What we we know that let's say Alice, what is the choices for Alice? Alice can either directly diverge from here, right? Like either go here or here, or Alice can first go here and then diverge, right? Or Alice can still go further and then choose to diverge, right? So these are the choices for Alice. So what we are seeing here, the pattern we are seeing here, there will be some prefix which will be common in Alice and Bob. That will cover all possible combination. So basically, either only this part will be common. Okay, let's say this red one denotes the one for Bob, the path for Bob, and this blue one denotes the path for Alice. So either this would be common in Alice. Let's say Alice took this path. So what is common between Alice and Bob? Only this node, right? So either this node would be common, or these two nodes would be common, right? Or these three nodes would be common, right? Either this or maybe this, right? So hope you can see the pattern here. Only a specific, only a particular prefix of path will be common between Alice and Bob. Bob has single path. So what we can do, we can just say that, okay, let's say like there are only few cases. Either this part will be common between Alice and Bob, or this path will be common between Alice and Bob, or this part will be common between Alice and Bob, right? So these are the three possible cases. Now let's try to solve for each of these cases. Let's say this part is common between Alice and Bob. Now if this part is common, what we are saying is we will not take this node at all from now onwards. So if this part is common, we can just take the maximum across the remaining children, right? So A has some children. We know the value of each of these children, and that's how we calculated the value at A. By value at A, by I mean what is the maximum gain of A if if A starts from here. So we already know what is the maximum gain if A starts from this node, let's say X, and we already know the maximum gain if A starts from this, let's say X dash. So we can just say if only this part is common, we can ignore the child which goes towards B and just take the maximum across the remaining child, and that would actually help us determine what which of these. So there are a couple of paths here, right? This is one path, this is another path, and this is another path, right? So basically if we just take the maximum across these two nodes, we can get the maximum across all these three paths. Agree? Because all these three paths are combination of like either it will go through this node, or it will go through this node, right? So we already know what is the maximum value if we start from this particular node, if a was here, and similarly we know what is the maximum value if this was the root. So we can just take the maximum across these two, and that would be the value, the maximum value of Alice if Alice choose to diverge from after this node itself. Okay, so that was the first choice. Now what is the second choice? Second choice is Alice decide to diverge after this. So these are the two things which are common between Alice and Bob. Now if this is the case, we will do a you will do the same thing again. You can, what you can say that, okay, at this node we are diverging, so this node will not be considered, because if this node was considered, then this statement that only these two node is valid, only these two node is common, is false, right? So this, we will just disregard this node and just take the value x here, and this will be the like total or the optimal income of A, of Alice, if these two node was common. Okay, and what is the last case? The last case is, let's say these all these three nodes are common between Alice and Bob, right? So if all these three nodes are common, what we are saying is these three nodes are there. Now just find me the maximum at this particular root, and you already know the value, you already know that particular value, right? So hope you get what exactly we are trying to do. What we have said is, because Bob has a single path and we have to calculate the optimal choice for Alice, we we have seen that Alice can share some path, some nodes with Bob. Now how many nodes Alice can share with Bob? I 1 2 3 4 up to the number of nodes that Bob covers, right? So if we consider all these cases one by one, we will be able to find out what is the cost for each of these possibilities. And once we we can just take the maximum across all of these possibilities. Okay, so just to reiterate, what we have done initially, we find out the maximum value at each of these root nodes. We have said that if this is the root node, what is the maximum value? If this is the root node, what is the maximum value? We already have that information. Now, once we have that information, we utilize that information in finding out what is the best path if some prefix here is common between Alice and Bob. Okay, so let's look at the pseudocode that will make things clear. So first thing is, you have to find this path, right? The path between Bob and root. So finding the path between Bob and root is very straightforward. You can just store the parent of each node, that you can do with simple DFS or BFS. Once you have the parent of each of these nodes, you can just apply a single while loop. Let's say the parent of root node is nothing, let's say -1. So you can just apply a simple while loop and just traverse through the parents. Like you will just do bob equals to parent of bob. So initially you will push this node, then you will push this node, then you will push this node, and finally you will be at -1. So you will break out of the loop. So by doing this, you are getting the path in the reverse order. Like first this, then this, right? But if you remember, we have to find the common prefixes. So common prefixes will be this or this or this, right? So you have to reverse the path first. So that's where you will reverse the path and then return. So this is the way you find out the path from Bob or any particular node to the root. Now once you have this information, the rest is very simple. What we discussed is, we will have some path common. So we will say that, okay, we know the path. Now either up till 0th index is common, up till one first index is common, or up till 2 index is common. So we just explore all those possibilities. Okay, now remember, there were three more conditions in the problem. The conditions was, if at a node Alice visited first, then Alice will get all the points. If at a node Bob visited first, Bob will get all the points. If at a node they both visited at the same instant they both get the points equally. So what we will do, because we are sharing some prefix, right? We will just we will just maintain the cost of that particular prefix. So we'll just say that okay, what is the cost up till now? So as we are incrementing, initially we'll consider up till zeroth index, then we will consider up till first index, and then we will consider up till two index. So as and when we are increasing the indexes, or taking on or increasing the common path between Alice and Bob, we will keep maintaining this cost. So we'll check if Alice reaches first at this particular node. How to check? Very simple. You can just like at any given point, Alice will take one step, Bob will take one step. So up till n by 2, all the nodes Alice will reach first. Up till last n by 2, Bob will reach first. And if there is a middle node, they both will get equally, or basically uh, there will not be any middle node in that case. The first n by 2 node is of Alice, the last n by 2 node is of Bob. So what we have done, as and when we are incrementing our indexes, we keep on checking whether Alice reaches this node first or not. If Alice reaches this node first, we give the entire contribution to Alice, which is this cost. Now if they both reaches there at the same instant, we will just denote we'll just give Alice the half value of of the current node. Now once, let's say you calculated the cost of this particular path. Now after that, the rest is simple. You just need to ignore one particular child and find the maximum across all the child. Let's say there are more childs here. You just need to find the maximum across all the child except the one that is going to B or to Bob. So let's say you wrote another function which says just take out the maximum across all the child except one child. So you can just pass the value of that child. So value of that child would be the next index. So current index would contain this node, next index would contain the next node, right? So you just pass out the value of next node. So what will be the cost of this particular prefix? You already know the cost of this prefix, right? And after this, you know the maximum cost across all the child except this node. So this will be the cost of this particular prefix. You will just take the maximum across all such indexes, and that is the answer. Okay, so this was a pretty uh, intense problem. You can just like the solution is not that tricky. It's just that there you just need to break the problem into pieces and then solve it. So I would encourage you, if you haven't got the entire solution, I would encourage you to rewind the video and watch it again. I'm very sure you will get it. And I would also encourage you to pause the video here and try to implement it yourself first. And if stuck, come back and watch the video again. So let's look at the code quickly. The code is very similar to what we discussed. We like these are just the variables that we declare. This is a graph or tree basically. This is the parent of each node, the value of each node, and best cost till leaf that we discussed, right? So we prepare the tree and the value. After that, we calculate the parent of each node. What is the parent of each node? Parent of each node is very simple. We just do a DFS, and as and when we are getting a child, we keep on populating its parent. That's it. That is very simple. Parent, calculating parent of each node. Now once you have parent of each node, like these two can be done in a single DFS as well. This is just for simplicity to make you understand things. So once you have calculated the parent of each node, you just need to find out the maximum path to leaf. Basically, this particular this particular algorithm that we discussed, right? So best path to leaf. So you just calculate this best path to leaf for each node. So you start at 0, again do a simple DFS. As discussed, if it is a leaf node, the value would be the value of the node. Otherwise, the value would be maximum across all the children plus the value of current node. Okay, so this is very similar. You can just go through it. Now, once you have a maximum path to leaf, you will find out what is the path of Bob. So how to calculate it? We discussed that we'll just keep on visiting the parent of Bob because we calculated the parent previously, right? Now, once you have the path to Bob, you will just figure out, or you will just iterate over all the common prefixes of Alice and Bob. So from zero up till a particular up till the entire path length. So as discussed, you will find out whether you will also maintain this cost till now value, which will denote what is the cost of the prefix that you have already taken, right? So let's say this is the common prefix that you consider. So you can just this cost till now will contain the value of this particular prefix, right? So if Alice reaches first, you will increment the cost. You will give the entire value to Alice. If they both have same arrival, you will give half of the cost to Alice because half will go to Bob. And if Alice doesn't reach first or they don't have the same arrival, it will go to Bob. So it there is no contribution to Alice. That's why there is not the next condition. Now once you have this, you will just do max result equals to maximum of previous results, like in previous prefixes, common prefixes that you have considered, and the cost till now, basically the cost of the prefix that you have considered, and then the maximum across all the children except one particular children. So maximum across all the children except a specific child, and that specific child is this one. Okay, and what is this find best specific best except specific child looks like? Very similar. We just skip if child is equals to the child to skip and take the maximum across all the other childs. Now there is one thing to notice here. If let's say uh, you let's say this was the B, okay, this let's say this is the B. Now and you consider this particular prefix, like entire path is this, and you consider this path as common. Now once you consider this path as common, you can't actually take any other child except this one, and this you already know that you can't take it, right? So for this particular case where you don't have any other child, you don't have to return 0 because 0 is a larger value. Here the nodes are negative as well, so you have to return very smaller value or minus infinity. That's where I have kept child count. If remaining child count is 0, right, we just return the value 0. Okay, so hope you got the solution. If you have any doubts in this entire solution, please post them in the comment section below. I would be happy to answer. If you like the video, give it thumbs up and do subscribe to the channel if you haven't already, and I will see you in the next video. Thank you.